so important. All right, main things we need to know about the mitochondria. We need to know inner membrane, outer membrane. Membrane space is important. I'm not so, like, if you drew it, like if you drew a simplified mitochondria, I don't really care if you label intermembrane space, but it is going to be relevant for what we're talking about today. Matrix and cristae. What is the cristae?
The folds.
The folds. So like this whole thing is the inner membrane, but each fold itself is a cristae. Why do you think the inside has all these folds? Instead of being like this.
There's more space.
Surface area. What happens in the inner membrane? What process? In your notes that you wrote down. Which one happens in the inner membrane? The electron transport chain. What is the main thing that the ETC is making? ATP. The main function of mitochondria is to make energy, right? That's its function. So the more surface area it has on the inner membrane, the more ATP it can make. If it was like this, it wouldn't make as much. It would be considered a what? A powerhouse. Right? Okay. Lovely, lovely. Questions before we get into all the details? It's going to be a long day. It's going to take most of class. We are going to take breaks.
Oh, really?
Sure. Sure. We are going to start. So find this page. Again, these circles, what do they represent? Carbons, right? So what's this beginning 6-carbon molecule? Glucose, right? So glucose, C6H12O6. So how many hydrogens are hanging off those carbons? 12. How many oxygens? 6. Can we see them? No, but they're there. So just keep it in mind. All these arrows and all the little packet that we're doing, what do the arrows represent?
Enzymes.
Enzymes. And it's a pathway of enzymes. Believe it or not, everything we're doing, even in photosynthesis now, is simplified for what actually is happening. Okay, so this one arrow right here, and we're saying it goes from this to this, it's actually a 5-step process. And we're just glossing over it. When you think I'm being harsh, I'm really being sort of nice. Okay? So, enzymes are doing this, enzymes are doing this as well. Where does glycolysis take place? In the cell. In the cytoplasm. Do all cells have cytoplasm? Yes. Okay? So if all cells have cytoplasm and glycolysis takes place in the cytoplasm, can all cells do glycolysis?
Yes.
Yes. The very first cells were what? What type of cells?
Okay.
Prokaryotic, right? So those very first prokaryotic cells on early Earth, what did early Earth look like? What? Extreme environment. So like think volcanoes, there's no greenery, there's no oxygen in the atmosphere, there's no way to support like life. Go. Okay? So early Earth. That's why this is an anaerobic process. It can occur when oxygen is present or when it's not present. It's just like, whatever. to glycolysis as an ancient process because it happened even in the very first cells. And then after endosymbiosis happened, it still kept happening. And it just became a part of this bigger cellular respiration mess we're gonna talk about. But from the dawn of time, glycolysis was happening. Do we have everything labeled? Thumbs up? Need 30 seconds? Need 30 seconds to do a midwit though. That's how we're gonna do things today. Alright. So glucose, we're gonna break it down into G3P. Where have you seen G3P before? Calvin cycle, when we were doing what? Making glucose. Right? So now we're just breaking it down. So we're gonna do this in two phases. The first phase is called energy investment. That's what this big E stands for, is energy. So with energy investment, we're gonna add energy into this. So we're gonna add 2 ATP. Because how many molecules of G3P are we trying to get to? 2. So we're gonna add 2 ATP in. When ATP comes in, what's it gonna drop off? Phosphate, always. Right, so it's gonna drop off our phosphates, 2 of them. And then it's gonna become ADP. So now we've had glucose, we've added in this energy, we've split it into 2 G3P. Now I'm halfway there. How many carbons are in G3P? 3. There's 2 of these, right? 1, 2. How many carbons in pyruvate? 3. Because there's 2 of them. Okay, that's why they're stacked. They're no longer together. This arrow, 6-point process. All we're saying is we're rearranging the molecule. Because are we getting rid of carbons at all? Nope, we're just reshuffling them. So in this reshuffling, this is what the phase is called energy payoff or payout or whatever you want to call it. But we're going to get energy out of this. So in this reshuffling, we're going to lose 3 things. The first of those is phosphates, plural. We're going to lose 4 of them. Remember the multi-step process? So we're going to lose 4 phosphates in the enzymes. We're also going to lose electrons and hydrogen ions. What's going to always pick up those empty phosphates? ADP. Okay, so we're going to have 4 ADP. They're going to come in, pick up those 4 phosphates, and we're going to make 4 ATP. Right? Energy payoff. We're getting energy out of it. Alright. In photosynthesis, let's go back briefly. What's our electron carrier?
NADPH.
NADP plus. Right? This is the carrier. This is what picks up electrons. In cellular respiration, there are 2 different ones. The first one being NAD plus. This one's going to carry high energy electrons. And the second one is FAD2 plus. And it's going to pick up low energy electrons. That's going to make more sense in a little bit. So we've got these 2 electron carriers. This will not be difficult to keep straight. If it's got a P, it's in photosynthesis. If it's lacking a P, then it's cellular respiration. So these electrons right here, they get dropped off, are high energy electrons. So what's going to come in and pick those up? NAD plus. So we're gonna have two NAD plus. It's gonna come in, pick up those electrons and hydrogen ions that get dropped off, and we're gonna make two NADH. Electron carriers, do they ever just get to hold on to their electrons forever? No, this is no different. So this NADH that's getting made is going to travel to the ETC. It has a purpose. And then after we reshuffle, lose all of these things, we're gonna be left with two pyruvate. Let's talk net products. What do I mean by net? The what? The finished, like, total amount. So how many pyruvates? How many? How many? I was hearing like 3 people answering. There's my bad. 2. How many NADH? 2. It's a tricky one. How many ATP?
2.
Why is it 2?
Because
Because 2 of these that get made over here have to come right back over here into energy investment. So we're only getting out of it 2 ATP. And those ATP are gonna go to the bank. They're gonna get stored. Now, is the bank a real place? No. It's just getting like held onto for the cell for any process that could take place that would need ATP. Alright, put your pencils down. Open your ears and your eyes. You're ready. Okay, glycolysis takes place in the cytoplasm and it's anaerobic. It's gonna take glucose. If this is happening in an animal cell, where do we get glucose? Food, plant, photosynthesis. Okay, so we're gonna take the glucose from either of those things and we're gonna break it down to our end goal of pyruvate. So it's gonna go through energy investment, where 2 ATP come in, add phosphates, and help to convert it into 2 G3P. Those 2 G3P have to get reshuffled into the pyruvate. So in that reshuffling by enzymes, we're gonna lose phosphates that get picked up by ADP, fake ATP, and we're gonna lose electrons that are high energy and hydrogen ions. So NAD plus comes in, picks those up, makes NADH. And we're left with 2 pyruvate that will go to pre-Krebs. We're left with 2 NADH that go to ETC and 2 HP that are going to the bank. I'm going to give you a minute and a half to turn to your seat partner and explain. Everybody practice.
I'm not gonna say anything. Alright, man.